Alright, our last section in chapter 1 is 1.5, infinite limits. Now before when we had limits that approached an unbounded number, we would say that those limits didn't exist, and today we are changing that and saying that these are becoming infinite limits. So just for a little bit reminder, here's our first example. This is what our function looks like. Or similar. Okay, so we are looking at right-handed and left-handed limits. If we were going to say that the limit, what is the limit at 2? We would say that it doesn't exist because we are unbounded. Now if we're looking at individual right-handed and left-handed limits, well, coming from the right, we are going up. We are going to say that's positive infinity. And if we are doing the left-handed limit, that's moving downward, so we're going to say that's approaching negative infinity. So we no longer need to say that doesn't exist unless, like I said, we're looking at just the number in general. Instead of a right-handed or left-handed limit, we can make them infinite. Okay, so here are all the graphs of the functions below. We're going to look at the right-handed and left-handed limits at 1 for each of these functions. Left and right. The left-handed limit of this one goes down to negative infinity, and the right-handed limit of this one goes up to positive infinity, I'm sorry. Now this one, coming from the left and coming from the right, they're both going up. So instead of writing the left and right-handed of this one, we can just say that it's positive infinity in general because they both approach positive infinity. Okay, part C. Coming from the left, we are going up, positive infinity, and from the right, we are going down to negative infinity. And the same thing that we did with part B, only this time in part D, they're both going down to negative infinity. So we don't have to write both limits, we can just say that limit as x approaches 1 is negative infinity. Okay, and obviously all 4 of those last examples, the reason we had infinite limits in the first place was because we were approaching a vertical asymptote. So now we're going to find vertical asymptotes of a function. The way we do that is if it's rational, we take the bottom half and set it equal to 0. Which we get -1. Now I drew the picture for you so you could see that it was -1, but we can now say, mathematically factual, that -1 is a vertical asymptote. Part C, from the picture we know that there's 2, but we're not necessarily sure what they are. So again, we take the bottom, set it equal to 0. This can be factored. And plus or minus 1, that's 2 vertical asymptotes. Cotangent is not a rational function, so it's not clear right away what we can set the bottom. We can't have a bottom set equal to anything. So we're actually going to rewrite it as cosine of x over sine of x, which we learned in trig, or the same thing. And then when we can set sine of x equal to 0, and if you think of the sine function, that's 1 period of sine, which means it has a 0 at 0, pi, and 2 pi. So every pi, you're going to have a 0. So for the cotangent function, you're going to have vertical asymptotes every n pi, where n is an integer. Okay, here we have a rational function with common factors. That means that we can find, right now we can find the factors at the top and the bottom and cancel some stuff to work it out. we have, if we were to look at the graph right now, the limit as we approach -2 from the left is negative infinity, and the limit as we approach -2 from the right is positive infinity. So we think that there's a vertical asymptote there, but we need to find if there's any other ones. We're going to factor the top, factor the bottom, see if anything in common cancels. Bottom is easier. Top is x plus 4, x minus 2. So that means that the x minus 2's cancel. And that's how we got that there's a vertical asymptote at -2. But we can't forget this x minus 2 over here. If we set that equal to 0, it doesn't give us a vertical asymptote. That gives us a hole. So we know that there's going to be a hole at x equals 2, and at x equals -2, there's going to be a vertical asymptote. So if you cancel a factor, it's not going to be not important anymore. It's still a hole. Okay. This function looks something like that. Find each limit. From the left, we're approaching positive infinity. From the right, we're approaching negative infinity. And that was it. Okay, some properties. So we have the limit as x approaches c of our function is infinity, and another function is a number L. If we were to add those two functions together, so basically infinity plus L, that's still infinity. If we multiply the two functions together, we're still going to get infinity, but that's only as long as L is positive. We will get negative infinity if L was negative. And this I need to flip around. G over F is going to be 0, because basically that's the concept of L over infinity, meaning there's such a big number on the bottom that your number is going to be so close to 0 that it's essentially 0. Okay, now I know these are not phrased well, and they're not actually asking a question, but I'm just illustrating those properties we just learned. If we know that the limit as x approaches 0 of 1 is 1, and the limit as x approaches 0 of 1 over x squared is infinity, if we add them together, we would get infinity. For b, the limit as x approaches 1 from the left is x squared plus 1 is 2, and the limit as x approaches 1 from the left of cotangent pi x is negative infinity. If we were to divide them, we would get 0. Not -0, still 0. And because the limit as x approaches 0 from the right of 3 is 3, and the limit as x approaches 0 from the right of cotangent is infinity, if we were to multiply those two together, we would get infinity, because the 3 was positive. Okay, and that is it for chapter 1.